Here these compounds A, B, C, D, these compounds are aromatic. Here, see here, compound B is aromatic. Compound E, this is aromatic because conjugate delocalization of bonds. Here this is aromatic because sulfur has sp2 hybridized orbital. Here it is aromatic. This is aromatic. And A and I, this is antiaromatic. It contains 4 pi electron. It contains 4 pi electrons, so it is antiaromatic. I, it also 1 2 3 4 5 6 here go 2 electron, 12 14 electron இருக்கிறதுனால இதுவும் வந்து antiaromatic. And C is non-aromatic. This is non-aromatic. And this is non-aromatic. And D is homoaromatic. And D is homoaromatic. நான் ஆல்ரெடி சொல்லியிருக்கேன். ஸோ இந்த மாதிரி ஐடென்டிஃபை பண்ணிக்கலாம். Here basicity of oxygen is more basic and more is the stable carbocation. For example, after polarization of ketonic double bond due to aromaticization, more is the equilibrium constant. Ka value பாருங்க 6.2, 31.1, 83.2, 117. Next, A is more acidic than B. Here you see. Now we come to organometallic aromatic compounds. In here you see organometallic compounds. Here it is a 5-membered ring which contains 2 double bond, 2 pi bond. Here it contains 2 pi bond. So totally 4 pi electron. Here 4 pi electron, and ferrous ion gives 2 electron. So totally it contains 12 electrons. So it is aromatic. Here it contains 12 electrons. It is aromatic. Now here you see this contains 3 double bond. Here it contains 3 double bond. Chromium gives 2 electron. So 6 into 2 12, 12 plus 2 14. Here this is also aromatic. Here you see it contains 2 double bond, so it is 4 pi electron and 2 electron from ion, so totally 6 electron, so it is aromatic. So organometallic compound la ellame vandu aromatic da vandu nama paakrom. Resonance energy of some aromatic compounds is given. Benzene 36, pyridine 32, thiophene 29, is pyrrole 21, furan 16. The resonance energy nalla paathu vechikanga. Resonance energy, the resonance energy கொடுத்திருக்கேன். Benzene, naphthalene பாருங்க, ring add ஆக resonance energy வந்து அதிகமாயிட்டே போகும். You take anthracene, this is phenanthrene. So if you add a ring, then the resonance energy goes on increases. Resonance energy number of cyclic ring, that is 36 by 1. Here 61 by 2, 2 ring இருக்கிறதுனால divided by 2, it is 30.5. இங்க 3 ring இருக்கிறதுனால 83 by 3, that is 27.7 per ring. Here 91 by 3, that is 30.3. Higher the resonance energy per ring, higher is the aromaticity of the molecule. You remember this point. Where benzene is having more resonance energy, benzene greater than naphthalene, greater than phenanthrene, than anthracene. Here the resonance structures are given. Now you take cyclooctatetraene. Tetraene 2 moles of potassium. You add 2K plus ion. Now it will give, you will get totally 10 electron, 4 pi bond equal to 8 electron. So here 2 electron, so totally 10 electron. Each moles of K gives 1 electron, so 2 electron from 2 moles of K to get aromatic. This compound is aromatic. Suppose it was treated with the H2SO4. We already seen that this get protonated. So plus ion, this is homoaromatic. And this cyclooctatetraene becomes homoaromatic when treated with H2SO4. When treated with K plus, it becomes aromatic. Similarly, this compound on heating gives the cyclooctatetraene thermal electrocyclic reaction, which is a non-aromatic compound. Now it is a non-aromatic. So this is the reactions correct. Now this you take this compound, you add 2 moles of K. Now you add 2 electron, totally 16 electron. 7 pi bond equal to 14 electron plus 2. So totally 16 electron, where this compound is antiaromatic. Now you take benzocyclobutadiene, where here this is aromatic, 6 pi electron, 2 pi electron, according to Huckel's rule. But when resonance occurs, this is aromatic, whereas this one is antiaromatic. According to Huckel's rule, it is antiaromatic if consider closed loop of 8 pi electron. Now we take azulene, non-benzenoid aromatic compound with a dipole moment. Some additional information: ways in which we can prepare aromatic compound. Now we take this compound, if you add C4H9Li, it becomes aromatic. You take this compound B treated with H2SO4, you will get this compound as aromatic. When this compound which is treated with silver, you will get aromatic. This compound treated with sodium hydroxide, you will get the compound, this is aromatic. Similarly, this compound, this becomes aromatic. So this compound gives aromatic compound. These are the ways to prepare aromatic. Now, neutral compound is tub shaped. SBFI, this is an important question asked, and gives an aromatic compound which gives to a dianion, which is an aromatic compound, dication which is planar. So this is aromatic. And hemoglobin is a part of hemoglobin that transport oxygen in the blood. This is aromatic. And porphyrin, which contains 18 pi electron, and this is aromatic. And this reaction, you see, in this reaction, it gives an compound where it contains 4 double bond, that is 8 pi electron, which is non-aromatic. And there was no conjugation. There was no conjugation of double bonds. So this is non-aromatic. Here, the same compound, when treated with palladium catalyst, now there occurs an conjugation, delocalization occurs. Here there is no delocalization, so it is non-aromatic. Here the delocalization of double bonds occurs. Now the compound becomes aromatic. You just remember this one. Next, Fulvenes type. When this fulvene is having exocyclic double bond which can be easily polarized. Now D is a donor atom, W is a withdrawing group, aromaticity decreases. If the double bond contains a donor atom means it is more aromatic. If it is a withdrawing group means chlorine, fluorine, like that, then it is the aromaticity will get decreased. Instead, for example, if we take 7-membered ring, the aromaticity increases. In this way, the aromaticity increases. In 5-membered ring, aromaticity decreases. You just observe the difference between these two. Now we come across Craig's law. This rule is applicable for polycyclic non-benzenide compound if the molecule contains C2 axis. Here it is a main condition, molecule should contain C2 axis. If it does not contain C2 axis means it does not obey Craig's rule. Total number of double bonds is n, is given as n, and calculate the value of n minus 1 which decides the aromaticity of the compound. If n minus 1, that is total n is the total number of double bond. If n minus 1 is an odd number means then the compound is non-aromatic. If n minus 1 is an even number then the compound is aromatic. For example, you take this compound here, this compound contains a C2 axis, n minus 1, it contains n minus 1 is a 4 pi bond is aromatic, that is n minus 1, 5, 1, 2, 3, 4, 5 double bonds. So 5 minus 1 is 4 which is aromatic. Now you take this system, it contains 4 double bond, 1, 2, 3, 4 double bond. So 4 minus 1 is 3. Now this compound is, according to Craig's rule, this compound is non-aromatic. Heptylene, n equal to 6, so n minus 1 is 5, it's an odd number, then so this is a non-aromatic compound according to Craig's rule. Annihilation effect. Each ring is fused system gives a part of aromaticity to the adjacent ring called annihilation effect. The number of benzene ring increases, aromaticity decreases. So that's all about aromatic compounds. We have discussed all the aromatic, non-aromatic, homoaromatic, antiaromatic, quasi compounds, dianion, and we have named most number of the compounds. Now here is this the exercise for you. Now you name which compound is aromatic and which compound is antiaromatic, which is homoaromatic and which is non-aromatic. You mark here. It is an exercise for you. Just note down these compounds, and these compounds I will give in the description box. You can download this exercise and you try it with yourself. For these compounds nearly I have given 30 compounds. You try it yourself and identify which is aromatic, which is non-aromatic, which is homoaromatic. You try it with yourself, and the document, PDF document which was attached and given in the description box. You can download from the description box. Thanks for watching this video. Thank you.